Welcome to our presentation for AISTATS 2023 on statistical contact tracing. We titled this paper "No Time to Waste" because in case of a new virus pandemic like we've seen in 2020-2021, we want to use the information at our disposal and have algorithms ready. So, summary: there need to be no convincing that pandemics are disastrous for society, as we've seen in 2020-2021, including lockdowns and such measures, and impact on economy. So there has been research establishing that statistical contact tracing can be better than manual or like just accounting-based contact tracing, and hence we submitted this research to this statistics-based conference, because now we can use statistics. Statistical contact tracing to inform, to both monitor virus spread and to also use this. To use this sort of statistics for quarantine policies. Existing algorithms, however, require hundreds or even thousands of high bit updates, and this research focuses on, running this inference algorithms with, both few updates and low bits. So we introduce a novel decentralized algorithm. It's based on an older algorithm from 2012 called factorized neighbors, and we show that this algorithm, as a sort of comparison to belief propagation, runs well for statistical inference in such contact tracing networks. I will emphasize we focus on decentralized algorithms. However, we leave the questions of and subsequent work will work on differential privacy. And we leave the questions of security to other work. Though we should say that it's decentralized and computations can happen encrypted. So the landscape is sort of as follows. Previous work established that statistical contact tracing can inform such testing and quarantine policies. And now we want to improve these statistical inference algorithms. They require tens to hundreds of messages, which is not impractical. So our method, to already foreshadow what we're going to talk towards, will need only 4 or 5 updates per day of a few bits, and that's something you can run practically. So our problem is to have our goal is to have low infection rate, low peak infection rate, and low communication budget, and we will focus on the peak infection rate because we would argue that. The consequences for society, these lockdowns and this, and hence the economic consequences, are from a peak in this infection rate. You could also optimize for hospitalization or total number of people infected, but this is just one metric one could choose. There will be 4 states in this model: susceptible, exposed, infected or infectious, or recovered, and the propagation model is such that the virus can only be transmitted in this I state, in this infectious state. This is a model misspecification because the true simulator we will use later uses 11 states, including asymptomatic patients and critical patients, for example. So we are definitely working on a model misspecification, but our argument is that even this statistical model with a few messages provides enough sort of signal to inform a quarantine strategy and a testing policy, and thereby could suppress the peak infection rate. The statistical model is a noisy OR model where we have a probability P0 of spontaneous infection and a probability P1, which models the probability of sort of transmission of the actual virus given a contact, because not every contact would involve transmission of a virus. And now we are at our best, right? Because we are a statistical conference, and now we have a model, we have a sort of metric established, so we need an algorithm. And as we want this algorithm to be decentralized, the algorithm, most of the algorithms are going to look like this structure. There's going to be incoming messages. Imagine them to be incoming COVID scores, and there's going to be incoming tests, and outputs are again COVID scores, where you might actually inform your neighbor or your contacts of your COVID score, and this could then later also then inform testing and quarantine policies. As inference algorithms, we compare Gibbs sampling, belief propagation, mean field variational inference, and then we use this. I mean, this old paper from 2012, which introduced this other algorithm for inference and probabilistic graphical models, which is called factorized neighbors. Firstly, to rule out variational inference grows exponentially in the number of contacts, which is infeasible. We did run it early on, and I mean, it does work, but because this scales exponentially, it's not feasible for realistic simulators. Which leaves us with belief propagation and factorized neighbors. First of all, we established that Gibbs sampling, or I mean, these are the updated equations for Gibbs sampling. These are the updated equations for belief propagation, and the new algorithm has these sort of updated equations, where you update the belief over a certain user using the beliefs over the neighbors, which are in this case contacts. And the name factorized neighbors is because this distribution is assumed to be factorized. And we work out these updated equations, and they turn out to scale linear in the number of contacts, which is very favorable. Because you could imagine a certain user visiting, a busy cafe or even a festival or a sports match, where one would sort of establish hundreds of contacts, and then running inference in that contact network. I mean, if it scales exponentially, it's just not feasible. We run results on 2 simulators, and also later on also a robustness study. The first simulator, which is this one, is a stochastic block model, and the simulator later is realistic based on sort of studies from that side of academia. But I mean, first things first, on the x-axis we have here the number of days where this sort of pandemic runs, and on the y-axis we have the infection rate. This is a simple policy where one uses the sort of output or the probabilistic inference or the posterior, and test the top people, the people with the highest score, and then put them into quarantine. And here we run this algorithm. So on the y-axis are infection rates, the thin lines are realizations, thick lines are population, mean or median, one of the two. And we show that this FN under low communication, has a lower infection rate already. Random policies where you put people randomly into quarantine. But we're going to study communication here. So here on the x-axis, because we argue now that from now on we're going to look at peak infection rate, so the highest infection rate over this course of 100 days. And we vary this over the communication load. So the random policy always has the same infection rate because it doesn't spend any communication. It's just plotted for reference. There's another paper, SIB, which was optimized for a different sort of testing policy. So here it doesn't do too well. But we show in this practical setting, and this practical setting we use the idea of a multiplier here. So it's the number of messages an algorithm needs to send per contact per day, multiplied by the number of bits in that message. There's established work that argue for a low number of bits. There's established contact tracing apps, which we cite in the paper, that argue for a low number of bits for these scores. Later on, due to security and privacy measures. So this practical setting we establish is 20. So this is either 20 messages of 1 bit, which is already a lot, then 10 messages of 2 bits, or which what we use for BP and FN is 5 messages of 4 bits. Both BP and FN in the number of lots of communication suppress this peak infection rate, down to 3%, say. Gibbs will also do this, but it's not shown on this x-axis because it needs a lot of messages because Gibbs has burn-in. We have our appendix has 2 results on that. In this practical setting, FN achieves a lower peak infection rate. Gibbs is slow, so it needs lots of messages before it has a low sort of posterior bias. We run 2 robustness studies where we either increase sort of the noisiness of the tests. So for example, let's say we increase a lot the false positive rate and the false negative rate, or phones would be still. And in both cases, we see that FN achieves a lower infection rate, peak infection rate compared to BP. We should say this is a pattern we will see later, that in the very noisy tests, both algorithms, decrease quite rapidly towards the random policy. So this is a point for later research, for future research, is why these inference algorithms cannot deal with noise, because that's actually the point where they turn out to be useful. A more realistic simulator is the OpenABM. It now uses more age categories, more occupations, household categories. At the start of this research, it already had more than 100 citations, more than 90 GitHub stars. So this is a simulator that's more realistic. Due to the nature of the simulation, the y-axis is now on the infection, or the y-axis is now on the log scale, where the x-axis is again on days to start this analysis, and for sending only 4 messages of 5 bits, fn suppresses this. The infection rate more than 2 orders of magnitude compared to most of the other approaches. Again, here we run the robustness results. Already we see in the starting scenario there's a way lower, because lower is better here, infection rate. Between the brackets are the 20 and 80 percentile of 20 random runs. In the still phone scenario, it's way lower. We should emphasize that in the noisy test, and this is something we want to analyze for later research, in the noisy tests, infection rates are still quite high. So this is something that should be worked on. One of the reviewers in the rebuttal period asked how, because in the original paper we had only 4 random seeds, but even if you run 10, or the previous table had 20 random seeds, this is sort of the pattern that you see. It is. So here you see the sort of noisiness. Discussion, and this is the last slide. The paper is titled "No Time to Waste." In the case of a new pandemic, we have no time to waste, so we should have these algorithms ready. A future work is how to establish algorithms that can deal with noisy tests, but mainly also differential privacy, which is the current work I'm working on. So how can we modify these algorithms? Again, let's start from the start. Gibbs sampling, variational inference or a variant, belief propagation, and these factorized neighbors. Can we modify these algorithms with certain noise processes, with certain other analyses to guarantee a form of privacy? And we are working now on differential privacy. So please come talk to us at the poster if you're interested in these topics. Code is available at this link, and my contact is this email address. So please reach out if you're interested in these topics. Thank you for your attention, and we hope to see you at the poster.